Hello everyone, welcome to the channel. In this video, we shall learn about Henry's law from the chapter Solutions. Henry's law deals with the effect of pressure on the solubility of gases in liquids. Almost all gases are soluble in water. The existence of aquatic life in lakes, rivers, seas and oceans is due to the dissolution of oxygen gas of the air in water. The solubility of a gas in a liquid at a particular temperature is expressed in terms of molarity or in terms of mole fraction of the gas. Solubility of gases is greatly affected by temperature and pressure. The effect of pressure is the most important factor influencing the solubility of a gas in a liquid. This effect was studied by William Henry in 1803 and he developed the Henry's law. It states that the mass of a gas dissolved in the given volume of a liquid at constant temperature is directly proportional to the pressure of the gas present in equilibrium with the liquid. Now, mathematically, we can write this as M is proportional to P, or M is equal to K into P. Here, M is the mass of the dissolved gas, P is the pressure of the gas, and K is the constant of proportionality whose value depends on the nature of the gas, the solvent, and the temperature. Now, Henry's law can also be stated as the solubility of a gas in a liquid at a particular temperature is directly proportional to the pressure of the gas in equilibrium with the liquid at that temperature. Now, if we express the solubility in terms of mole fraction of the gas in the solution, now for any gas A, Henry's law can be written as Chi A is equal to K into Pa, where Chi A is the mole fraction of the gas in the solution, Pa is the partial pressure of the gas above the solution, and K is the proportionality constant whose value depends upon the nature of the gas, the solvent and temperature. Now this equation can be rewritten as Pa is equal to Kh into Chi A. Here, Kh is also known as Henry's law constant. This is the most commonly used form of Henry's law, and it can also be defined as follows. The partial pressure of a gas in vapor phase is directly proportional to the mole fraction of the gas in the solution. Some of the characteristics of this Henry's law constant Kh are: Henry's law constant is a function of the nature of the gas. The greater the value of Kh, the lower is the solubility of the gas in the same partial pressure at a particular temperature. The value of Kh increases with increase of temperature, implying that solubility decreases with the increase of temperature at the same pressure. Some of the important applications of Henry's law are in the production of carbonated beverages. Now, to increase the solubility of carbon dioxide in soft drinks, soda water as well as beer, champagne, the bottles are sealed under high pressure. When the bottle is opened to air, the partial pressure of carbon dioxide above the solution decreases. As a result, solubility decreases and hence carbon dioxide bubbles out. Another important application is in deep sea diving. Now, deep sea divers or scuba divers depend upon the compressed air for their oxygen supply. According to Henry's law, the solubilities of gases increases with pressure. Thus, both nitrogen and oxygen will dissolve considerably in the blood and other body fluids. Oxygen is used up for metabolism, but due to the high partial pressure and greater solubility, nitrogen will remain dissolved and will form bubbles when the diver comes up to the atmospheric pressure. These bubbles affect nerve impulses and give rise to a disease called bends or decompression sickness, and this may lead to even death. Another important application of Henry's law is also seen in the case of high altitude mountain climbers. At high altitudes, the partial pressure of oxygen is less than that at sea level. As a result, there is low concentration of oxygen in the blood and tissues of these people, and consequently they may feel weak and unable to think properly, and this is called as anoxia. Now, to complete this discussion, let us go through a few numericals or problems based on Henry's law. Let us discuss this first problem. Now, in this question, you can see if nitrogen gas is bubbled through water at 293 Kelvin, how many millimoles of nitrogen gas would dissolve in 1 liter of water? And here it is assumed that nitrogen gas exerts a partial pressure of 0.987 bar. And it is also given that Henry's law constant for nitrogen at this temperature is 76.48 kilobar. Now, for the first part of the question, we simply have to calculate the mole fraction of nitrogen based on the values given for partial pressure and Henry's law constant. So here we see that the mole fraction of nitrogen is equal to 1.29 into 10 power minus 5. Now, coming to the second part of the question, we have to calculate the millimoles of nitrogen gas that would dissolve in 1 liter of water. So here, quite simply, we have to, in the second part of the question, we have to calculate the number of moles of nitrogen that is present in 1 liter of water. So here we can write the relation for mole fraction of nitrogen as number of moles of nitrogen divided by the total number of moles in the solution, that is the number of moles of nitrogen plus the number of moles of water. Now, number of moles of water is equal to 55.5. I will show you this relation, how we derive this value later on. So it is seen that the concentration or the mole fraction of nitrogen would be very, very less compared to the mole fraction or the concentration of water in the solution. So it is assumed that the total number of moles in the solution would be equal to the total number of moles of water. So applying this in this relation for the mole fraction for nitrogen, we would see that we would neglect the number of moles for nitrogen. So in this case, by putting the values of the mole fraction of nitrogen that we have calculated earlier, we see that the number of moles for nitrogen is 0.716 millimoles. Now, how did we come about this value for the number of moles for water? Now, here we assume that the density of water is 1 gram per centimeter cube. So this means that if we calculate the mass of water by simply multiplying the volume of water and the density of water, so volume we know that it is 1 liter, so that means it is 1000 centimeter cube, and density of water is 1 gram per centimeter cube. So the mass of water we find is 1000 grams. So in calculating the number of moles, we see that now number of moles, as we know, is mass by molar mass. So we simply apply that for this for water. So it is equal to the mass of water divided by the molecular mass of water, which comes out to be 55.5 moles. Now let us discuss the second type of problems based on Henry's law. Here the question is, at what partial pressure oxygen will have a solubility of 0.05 grams per liter in water at 293 Kelvin? And they've given us the value of Henry's law constant for oxygen in water at 293 Kelvin, which is 34.86 kilobar, and we have to assume that the density of the solution to be the same as that of the solvent. Now, in this case, as you can see, the solubility of oxygen in water is given in terms of grams, in terms of grams per liter. So that means we have to first express this solubility in terms of mole fraction, and then only can we find out the partial pressure of oxygen by applying the Henry's law equation. So in this case, firstly, what we can find out from this question is that we can see that the volume of the solution is 1 liter, or it is equal to 1000 ml, and therefore we can find out the mass of the solution by multiplying the volume of the solution into the density of the solution. Now, as mentioned in the question, the density of the solution is the same as that of the solvent, that is the water. So here we assume that the density of the solution is also 1 gram per centimeter cube. And by doing so, we find that the mass of the solution is 1000 grams. Now, we can also calculate the mass of the solvent, that is the mass of water in this solution. Here we see that the mass of water is 1000 grams. So we can find out the number of moles of water and that of oxygen, and by doing so we can also calculate the mole fraction of oxygen. Now here we know that since the amount of gas in the solution is very less, so it is assumed that the number of moles of oxygen is very less, and hence the total number of moles is nearly equal to the total number of moles of water. So here we find that the mole fraction of oxygen is equal to 2.81 into 10 power minus 5. Now putting this value in the relation for Henry's law, we can find the partial pressure of oxygen, and here it is found out to be 0.98 bar.